Could you explain where that comes from for our?
Oh, that's a long story. I mean, it came from the fact that we have a very small cosmological constant in our universe. So the cosmological constant is the energy density of the vacuum. You might find it funny that the vacuum has energy, but it does. And in fact, what's funny is not that it has energy, but that it has so little. Why is that funny? Because we have great theories that are otherwise well tested and work super well, like the standard model of particle physics, which tell us that there are many contributions to the energy density of empty space, all of which are like 50, 60 orders of magnitude larger, at least, and that's just based on which part of the theory we're confident about, than the observed value. So you have to explain why all these contributions cancel to such a ridiculous precision, and moreover, why they cancel to this precision now, as opposed to, for example, in the early universe, where those contributions would have been completely different. Because, say, electroweak symmetry breaking wouldn't have happened. That would have changed the equations completely. And so the cosmological constant must have actually been quite large in the early universe. What's going on? What is making this happen? And it's not a symmetry, because if it were a symmetry, then that symmetry should be glaringly obvious to us. The energy scale that's associated with the value of the cosmological constant is extremely low. It's not something that we haven't built strong accelerators yet to sort of explore. It's like you can, it's a nothing energy scale. It's a joke. We know there's no symmetry. So the proposal that had been sort of floating around for a while, due to Weinberg and many other people were thinking about it, is maybe the cosmological constant is a kind of random variable that can take any value, and maybe it's like different branches of the wave function have different values of the cosmological constant. Maybe different parts of the universe have different values. I don't know. There weren't any good models for it that didn't run into other problems like producing an empty universe. But the basic idea was that perhaps the smallness of the cosmological constant has to be explained by a combination of finding a theory where it can take on many different values with an anthropic argument, saying, well, now what selects for the presence of a small cosmological constant is the fact that observers can't live in places with a large cosmological constant. That was an argument that Steve Weinberg tried to make pretty accurate by showing that the formation of galaxies is quite sensitive to the value of the cosmological constant, and if it was like 10 or 100 times larger, there'd be a lot fewer galaxies. And so what Joe and I did was sort of to solve the two problems around this at the time rather vague idea, I think. One is to have your theory give you lots of different values that the cosmological constant could take in principle, and the other was to make sure that those are somehow populated and that the universe can find a way to reach all these different values without first getting completely empty. That there's a sort of general problem if you try to sort of reach a small value of the cosmological constant in a targeted way rather than just by accident. You first have to empty out the universe, because only gravity knows what the value of the cosmological constant is. Nothing else measures absolute values of energy in the world. And gravity is distracted by all the other stuff that's around. So that doesn't work. So you have to just make everything. And so we pointed out that the string theory has all the ingredients. It has a lot of extra dimensions, traditionally regarded as maybe a bit of an embarrassment. You have to say, oh, well, they're all curled up. There's like 6 or 7 extra dimensions that are curled up so as to explain why we haven't seen them. And then there's so many possibilities how they could be curled up. I don't know. It doesn't look like a very unique theory anymore. And we kind of just leaned into that and said, yeah, exactly. It's not unique at this effective low energy regime at which we find ourselves. Just like the standard model can make 100 different elements, and out of those elements you can make uncountably different combinations of like molecules and how you could arrange them, right? Just think of protein folding, and to say nothing of the macroscopic world. The numbers are unimaginably large of just combinatorics you get, the possible things you could do. Maybe the way that our world came from string theory works the same way. That, you know, there's, and we did some combinatorics. We showed that the kind of ingredients that Joe had recently discovered, D-branes, can be arranged in different ways in these extra dimensions. They give rise to something called fluxes, somewhat analogous to electric fields. And you can estimate how many different ways can you go down from the 10-dimensional sort of fundamental description of string theory, which would still be quite unique, to making stuff. Making, for example, a 3+1 dimensional world with curled up dimensions. And we found the numbers are enormous. It could easily be 10 to the 500. Estimates vary. The point isn't exactly how much. The point is, you're thinking of the vacuum that we see around us as not a particularly profound, deep fundamental thing, but like one arrangement of some fundamental ingredients, and there could have been many other arrangements. And we argued in particular that the spectrum or the possible values of this cosmological constant that is so remarkably small where we live, indeed can be very fine. But because of the way that these vacua are arranged in string theory, you can find a vacuum like ours without first emptying out the universe. You don't have to go step by step by step by step to smaller values of the cosmological constant as you had to in some early models that tried to realize Weinberg's idea. You get to sort of move around in a multi-dimensional landscape where most likely our parent vacuum actually had an enormous cosmological constant. The arrangement is pretty random. And so you can come down with a lot of energy to spare, and you can make the Big Bang, as we usually think about it, would just be the decay of our parent vacuum into ours, and there's enough energy to go around to heat the universe up and give you a hot Big Bang and actually make the model consistent. That was really the big obstruction, making the model consistent with standard cosmology.